In this video, I want to show you how to access old AP Chemistry exam free response questions on the College Board website and go through one with you. So first, let's see how we can access these. So if you start at the AP Central page, which is just apcentral.collegeboard.org, and then you go to AP Courses and Exams, you go Course and Exams, Pages, Science, AP Chemistry. And so in one video I showed you that I click here to go to the course and exam description to find out more information about the exam and about the curriculum that is sort of fair game for the exam. But here I'm going to click on this tab, the exam, and this gives a lot of information about the exam, some of which I've gone over in my video on the composition of the AP Chemistry exam. So it has the exam date, it has the format, which I went over in that video, calculator policy, and then it has old free response questions. Unfortunately, the College Board does not release old multiple choice questions. So for that, you will want to I recommend getting the Princeton Review. I think they have the best practice multiple choice questions that most align with the AP Chemistry curriculum and are designed similar to the problems that will be on the test. For example, they give you calculations that can be done without a calculator, like they are on the actual test. Some of the other review books that I've seen aren't really either styled correctly or they include extra material that's not actually in the curriculum. So I do recommend the Princeton Review, and they have good free response questions as well, but really the best source of preparation is these old free response questions because they're directly from the College Board who makes the AP test. So if you just want to look at the 2021, last year's, they have it here, but they also have other ones if we click on past exam questions. And here they have, again, 2021, and basically all of them since 2014, other than 2020, when the exam was different due to COVID. So I'm just going to go through number one of the 2019 test today, in this video, and then I'm going to make a separate video going through how to kind of grade your own response using the answer key and then looking through student responses. And this is a exercise that I recommend doing, but I'll focus more on that component of the exercise in another video. This video, I just want to show you, first of all, how to access these free response questions and then just go through one with you. Okay, so if we click here, this is the 2019 FRQ, and we see that they give us a periodic table and a formula sheet, the same that you'll get on the multiple choice section. Okay, but the difference is we can use a calculator, and we will want to use a calculator for this, the free response section. And okay, I talked about this in my video about the AP exam composition, but it states it here as well. So there's 7 questions in the FRQ section worth a total of 1 hour. You have 1 hour and 45 minutes to do them all. The first 3 questions are what are called long free response questions, worth 10 points each, and they suggest taking roughly 23 minutes per these questions. And then questions 4 through 7 are what are called short free response questions, worth 4 points each, and then they recommend taking about 9 minutes per those questions. Okay, now note, it also says, for calculations, clearly show the method used and the steps involved in arriving at your answers. You must show your work to receive credit for your answer and pay attention to significant figures. So yeah, basically always show your work and then round your final answer to the proper number of significant figures, and with the correct units if applicable. So just to show you quickly kind of what the difference between what a long free response and short free response question are. So let's just briefly skim through this, and then we'll go through number one in more detail after that. So we see like this has A, B, C, D, E, F, G, H. So that's like what? 1, 2, 3, 4, 5, 6, 7, 8 parts. So that's really the difference, is just kind of how many parts there are. But each individual part is not necessarily longer on the long FRQ than it is on the short FRQ. There's just more parts to it. And then this one is, the first three are long FRQs. So this has 1, 2, 3, 4, 5, 6, 7 parts, I think. 1, 2, 3, 4, 5, 6, 7, 8. So yeah, generally most of them will be around 7 to 8 parts for the long FRQs. And then the shorter ones, this one has 4. This one has just 2, although this one is kind of 3 if you want to count it like that. 2, oh, actually 3, and then 4. So yeah, I mean, generally these are between 2 to 4 parts, the short FRQs. Okay, but I want to go through number one in this video, and want to kind of highlight a couple things. Partially just kind of how to format your answers to these, so kind of in general how to approach free response questions and how to answer them. And then also, hopefully we'll touch on some concepts, some chemistry concepts in that process. So I cannot write directly on this document, so I've copied this into a Word document, and yeah, we will write our answers on here. Let's make this bigger. Okay, so the compound urea, shown above, is widely used in chemical fertilizers. The complete electron dot diagram for the urea molecule is shown above. Identify the hybridization of the valence orbitals of the carbon atom in the urea molecule. Okay, so it's the hybridization of the carbon atom. So let me make sure I have this. Okay, there we go. So we're looking at the carbon atom, which is right here. And also note, it just says identify. So if it just says identify, that's all you need to do. You do not need to write a sentence. You do not need to TQAA. You do not need to explain your answer unless it asks you to. In this case, it just says identify. So that's all you need to do. So basically, if you don't remember, to identify hybridization, you want to count the number of electron domains around the atom that you're identifying the hybridization. So this carbon has 3 electron domains. Because it has three bonding domains. A double bond counts as 1 bonding domain, which counts as 1 electron domain. So there's 3 bonding domains, and there's no lone pairs on the carbon atom, which, remember, if there were lone pairs, those do count as electron domains, so we would have to take those into consideration, but the carbon atom does not have any lone pairs on it. It only has 3 bonding domains, so a total of 3 electron domains. Okay, so basically that's what you use to determine the hybridization is the number of electron domains. 3 electron domains is sp2 hybridized. Basically, you just count the exponents, because really this s is s1. So 1s and 2p gives you a total of 3. Okay. If you had 2 electron domains, that is just sp hybridized, and if you have 4 electron domains, that is sp3 hybridized. And as I talked about in my video about what will and won't be on the AP test, these are the only hybridizations they ask about, sp, sp2, and sp3. Because when the d orbitals become involved, it's actually kind of complicated, and there's actually some debate in theory as to how they actually participate in hybridization. So they're only going to ask about these 3 types of hybridization, and it's really just depending on the total number of electron domains around the central atom. Okay, so for example, the nitrogens, in this case, if it asked about those would be sp3 hybridized, because those have 4 electron domains, 3 bonding domains, and 1 lone pair. Okay, the carbon, though, is all it's asking, so this would just be sp2, and that's all I need to write, again, because it just asked me to identify it. Okay, so all this other stuff I wrote, that was just to help you guys, but you do not need to write any of that in your answer. You just need to put sp2. Okay. So the next thing, I'm going to erase some of these little stuff so it's not so messy. Okay. Urea has a high solubility in water, due in part to its ability to form hydrogen bonds. A urea molecule and 4 water molecules are represented in the box below. Draw one dashed line to indicate a possible location of a hydrogen bond between a water molecule and the urea molecule. So remember that a hydrogen bond is a type of intermolecular force. So it has to be between separate molecules, and it has to be between a H of one molecule and then an N, O, or F of another molecule. Now in this case we don't have any Fs, but we have an N and an O. So for example, this would be a hydrogen bond because it's between, they're telling us this is a hydrogen based on the key, and this is an oxygen. So that would be an example of a hydrogen bond. So would this. And yeah, I mean, so would this. And then you could even have, you know, something like this between the N and the H. That would also be a hydrogen bond. Now it specifically asks for only one, so I'm going to erase some of these other ones so that they don't mark me wrong for putting more than one. I don't know if they would do that, but basically, I guess main thing is follow the instructions. So if they tell you to identify, just identify. If they tell you to just draw one, just draw one. Don't do more than they ask. Okay. So I am going to, yeah, I'll just leave that one. But hopefully that makes sense how you do that. Okay. And then the dissolution of urea is represented by the equation above. Okay, I probably should have moved that down, so let me just copy that below. That's our equation. The dissolution of urea is represented by that equation. A student determines that 5.39 grams of urea with a molar mass of 60.06 grams per mole can dissolve in water to make 5 milliliter milliliters of the saturated solution at 20 degrees Celsius. Calculate the concentration of urea in moles per liter in the saturated solution at 20 degrees Celsius. Okay, so concentration is in moles per liter, or this is a molarity. So what I know my grams of urea, and I know the volume in milliliters in my solution. So I'm going to convert grams to moles using the molar mass that they've provided me. And I'm just going to write urea so that that's simpler for me, and I don't really need the chemical formula since I don't need to find the molar mass. They've already given it to me. And even if you, what I would recommend is even if you do know how to find the molar mass, if they give you a molar mass, or anytime they give you a number, even if you know like a different number that's kind of slightly different, just use the number that they gave you. Now, if they didn't give you the molar mass, then yes, you have to find it on the periodic table. If they give you a molar mass, don't bother calculating it on your own. A, because it's a waste of time, and B, if they give you a number, they probably want you to use that specific number. So when you calculate it, if you may get a slightly different number just due to rounding, which is probably not that big of a deal, but there's just no need to do that. Just use the number they gave you. So the number they gave me is 60.06 grams per mole. So when I do this, I get, and you are allowed a calculator on this part, so you don't need to round anything, so you can use your calculator, and we get 0.0897 moles of urea. Okay, and then 5 milliliters, we need to convert that to liters. So divide by 1,000. You probably don't have to write out this step if you don't want to, but I would at least show the value in liters. So I would at least show the next step, which I'll get to that in a second. So this is going to be 0.00500 liters, and then I would write out that molarity is equal to 0.0897 moles over 0.00500 liters. And okay, so we get 17.9 molar. For part C. Okay. And you do need to show your work, so you would want to show pretty much all of this. Again, you can maybe skip the step where you're showing your conversion from milliliters to liters, but certainly everything else you would want to show. Okay. So D says the student also determines that the concentration of urea in a saturated solution at 25 degrees Celsius is 19.8 molar. Based on this information, is the dissolution of urea endothermic or exothermic? Justify your answer in terms of Le Chatelier's principle. Okay, so we calculated the concentration of a saturated solution at 20 degrees Celsius. They're telling us that the concentration of a saturated solution at 25 degrees Celsius is 19.8 molar. So basically what that tells us is that when we increase the temperature, we can dissolve more of the urea because the molarity of it is higher in the saturated solution. So so it tells us that we want to justify our answer in terms of Le Chatelier's principle. So here we are going to need to write an explanation. We're going to need to answer the question and then write an explanation because it's asking us to justify our answer. So we want to start thinking about equilibrium. So we have an equilibrium reaction above, and basically we have more of this because the molarity of it is larger. The molarity is of the aqueous, not the solid, because the aqueous is what dissolves in water. So that means that when we increase the temperature, the equilibrium shifts to the right. So then the question is, does that mean it's endothermic or exothermic? Well, remember, endothermic you can think of as heat is a reactant because heat is being absorbed. And then exothermic you can think of heat is a product because heat is being produced or released. So ask yourself, if I write heat on the left side and I increase the heat, according to Le Chatelier's principle, that is going to shift the reaction to the right, which is what happens. So that basically is the correct answer. If I had written heat on the right side, as a product, and I add that, then according to Le Chatelier's principle, it will shift to the left. So that is not what happens because we get more dissolving. So that is not the correct answer. Okay. Okay. So now we want to think about how to explain this. And I think it would be okay to even write kind of this reaction out, like with heat on the left side, to help you with your explanation. But let's see how I want to explain this. I'm gonna scroll down, I guess, and type it down here. So I would start by saying the concentration of urea in the solution is greater at 25 degrees Celsius than it is at 20 degrees Celsius. This means that the equilibrium reaction, aqueous, shifts to the right when temperature is increased. That indicates that the reaction is endothermic, because for an endothermic reaction, we can write heat as being a reactant. And here you may want to actually again write out this equation up here with the heat involved. I think that would be perfectly acceptable. I wouldn't just write the equation. I would write at least a couple sentences more than that, but I definitely think that would be fine to include somewhere in your answer to help your explanation. Okay. You could probably get away with it without actually writing the equation too, as long as you explain it thoroughly, which is kind of what I'm trying to do here. So that indicates that the reaction is endothermic, because for an endothermic reaction, we can write heat as being a reactant. Then, if we increase the temperature, okay, which is like adding heat, then according to Le Chatelier's principle, the reaction will shift to the right. And this is consistent with the data. Okay, so I think that's a pretty good explanation for that question. All right, so then E says the equipment shown above is provided so that the student can determine the value of the molar heat of solution for urea. Knowing that the specific heat of the solution is 4.18 joules per gram per degree Celsius, list the specific measurements that are required to be made during the experiment. Okay, so again, I want to point out that it just says list. Okay, so always pay attention to the action verb in these questions. So in A, the action verb was identify. In B, it was draw. In C, it was calculate. In D, well, the first part of the D did not really have an action verb, it just asked a question. And then it said justify. And then now E, it just says list. So again, we do not need to explain our list. We just need to list specific measurements. Now, I am going to explain it so that you understand my list, but I'm just showing you that you don't need to. Now, if you need to write stuff out to help you answer the question, that's fine, but you don't need to write an explanation. You just need to list it. Okay, so let's think about how will we calculate the molar heat of solution for urea. Well, molar heat of solution is going to be in joules per mole, or kilojoules per mole. That's why it's called the molar heat, because it's per mole. So one thing we're going to need is we're going to need the moles of urea. Now, there's no way to directly measure moles. We don't have any mole measurer provided to us. But we do have a balance. Balance measures grams, or mass. So one thing we can think is that if we can measure the mass of urea, we know the molar mass, we can convert that to moles. So that's one thing we're going to want. We're going to want the mass of urea. Now the question, though, is can we directly measure that? That's another thing we have to think about. Is there a way to directly measure the mass of urea? And in this case, there's really not, because we don't want to put the urea directly on the scale. Okay, now if we had like a filter paper or a weigh boat, we could do that, but they're not telling us that we do have any of that kind of stuff. And I don't want to assume that we do. So while we do want the mass of urea, we're going to have to do kind of a roundabout way of finding it. We're not going to be able to directly measure the mass of urea. So I'm not actually going to put this in my list, because again, it's not something we're going to directly measure. And we only want to include stuff that we're going to directly measure. So let's think a little bit more about what we're going to do in this experiment. What we're going to do is we're going to take some of this distilled water. We're going to take some of this distilled water and put it in this cup. And then we are going to put this thermometer in here, and we're going to measure the initial temperature of water in cup. And then we're going to add some of the urea to the water in the cup. And what we would expect is that the temperature of the water would change, because that's really what we're measuring with heat of solution, is how much heat is absorbed or released when something dissolves. And we would expect in this case heat to be absorbed by the urea, because we proved above that it was an endothermic process. So we want to measure the final temperature of water in cup. And I'm going to specify what I mean by the final. So I mean after the urea is added. Okay, now what we want to know how much heat is absorbed or released. And we're going to do that using this equation, Q equals mc delta T. So we've already covered the delta T part, because we measure the initial and final temperature, so we can calculate the change in temperature. We already know the C, that's the specific heat, that's this. But we need now the mass of our solution. Okay, so that's basically containing water and urea. So we can measure that using the balance, but we have this cup here as well. We have this it's in this polystyrene cup. We can't remove that cup. So what we want to do before we put anything in it is we want to measure the mass of just the cup. Okay, and then I'm going to measure the mass of cup plus water after I've put some water in the cup. So then the difference between these would give you the mass of just the water. And then I'm also going to measure the mass of the cup plus the water plus the urea. And this is actually how I'm going to get the mass of urea. So this is going to be equal to this minus this, if that makes sense. Actually make more sense if I drew this like this. So this mass of urea will be equal to the mass of the cup plus water plus urea minus the mass of the cup plus the water. So that's what I'll use to find the mass of the urea specifically. But then I'll also want the mass of my solution, which the solution is this entire thing. That's my solution. That's what I'm going to use here. So to get that, I'll take this third mass minus the mass of just the cup. Okay, but I need to record each of those three masses to give myself the various masses that I'm going to do, that I'm going to use. Okay, and then again, we'll use this equation to calculate Q, and then we'll divide by the moles of urea to find the molar heat of solution, which to do that we'll need to convert the mass to moles using the molar mass. But you don't need to describe in this question. It's not asking you to describe the entire process. It's just asking you to describe list the measurements you'll need. So those would be these two, and then these three here. And we can measure all of those with the equipment we have. We can use the thermometer to measure the temperatures, and then we can use the balance to measure all of the masses, and in each case we have a cup to hold, all those masses. So make sure if you have a question like this, don't just put mass of water, because you're not just pouring water directly on the balance. Okay, you're not directly measuring that. You may want to know what that value is, but you can't directly measure it. We have to measure the mass of the cup by itself, and then the mass of the cup plus the water, and then the mass of the cup plus the water plus the urea. That's what we have to measure, okay, to obtain the values that we want. Okay, hopefully that helps. So the next question, the entropy change for the dissolution of urea, which remember is just this reaction above here, is 70 joules per mole per Kelvin at 25 degrees Celsius. Using the information in the table above, calculate the absolute molar entropy of aqueous urea. So this is just basically going to be part F. I'll write this. It'll just be easier for me to write rather than type. Delta S of reaction is equal to the sum of the delta S, or actually this is not delta S, this is just S, of the products minus the sum of the entropies of the reactants. Now you probably don't necessarily have to write this equation out, but this is the equation we're going to use, and this equation is on your formula sheet. So if we scroll up here, it's right here. That's the equation we're going to be using. Okay, so our delta S of the reaction, we're told that's this, the entropy change for the dissolution of urea for that process is 70.1. Is equal to products. Well, the aqueous, that's the products. We don't know what that is. So we get the entropy of H2N CO NH2 aqueous minus the reactants, which is the solid, which is 104.6. Now keep in mind, if you had coefficients here, you would need to include you would need to multiply the entropies by the coefficients, but in this case, both of our coefficients are just 1, so we don't need to worry about that. So I add 104.6 to both sides, and I get 174.7, and this was joules per mole per Kelvin. That's the standard entropy of aqueous urea. Okay, G, using particle level reasoning, explain, so we need to explain now why delta S of the solution is positive. Okay, well, anytime the change in entropy is positive, sorry about that, if the delta S is positive, the change in entropy is positive. That means the entropy is increasing. And this makes sense because we're going from solid to an aqueous. So in a solid, it's a crystal structure. There's more order to it. And then in when it dissolves, we're breaking some of those intermolecular forces holding the urea molecules together. And so there's a higher degree of freedom. So I'm just basically going to describe that. So I'm going to say delta S for the solution is positive because the system is becoming less ordered when the urea molecules dissolve in water. This is because the intermolecular forces between urea molecules in the solid phase are being broken, and the urea molecules have a greater degree of freedom. Okay, so thus the entropy of the system is increasing during the solution process, so the change in entropy, which is delta S, is positive. And this goes for any solution. Anytime something is dissolving, the entropy is increasing for this reason. Okay. And then lastly, part H asks, the student claims that delta S for the process contributes to the thermodynamic favorability of the dissolution of urea at 25 degrees Celsius. Use the thermodynamic information above to support the student's claim. Okay, so basically we have to support this claim that the delta S contributes to the thermodynamic favorability of this process, and we need to use thermodynamic information provided to support that. So basically, anytime you see thermodynamic favorability, you generally want to think about delta G. So if we think about the equation, delta G equals delta H minus T delta S. Now we know that when this is negative, that the reaction or the process is spontaneous, is normally how this is taught, but we can also refer to it as thermodynamically favorable, which is probably a better way, honestly, of describing it. Just means that the forward process is favored. It will occur naturally on its own, although it may or may not take a long amount of time. It says nothing about how quickly the process will occur, just that it will occur naturally without any outside intervention. So, what I would use to describe or to justify why the entropy does contribute to this process being thermodynamically favorable is that the delta S is positive, which we are told that it is. The delta S, I mean, it's right here. Delta S of the process is positive. So according to this equation, well, T is always positive because it's in Kelvin. So according to this equation, when delta S is positive, we are doing delta H minus a positive number. So that means that the T delta S term is making delta G more negative, okay? Or in other words, more thermodynamically favorable, okay? If delta S were negative, then we would be subtracting a negative number, which would be making delta G more positive or less thermodynamically favorable. So that's basically what I'm going to describe. So I would say the student is correct that the delta S of the reaction contributes to the thermodynamic favorability of the reaction because the delta S of the reaction is positive. According to the Gibbs, I'm not quite sure the correct, I think this is the correct punctuation or apostrophe use, but I'm not entirely sure. According to the Gibbs equation, which is this equation, delta G equals delta H minus T delta S, according to the Gibbs equation, when delta S, well, I'll just say a positive delta S makes delta G more negative. It doesn't necessarily make delta G negative, because delta G also depends on the value of delta H, okay? So a positive delta S does not guarantee that delta G will be negative, but it makes it more negative than if delta S were 0 or if it were negative. Hopefully that makes sense. So a positive delta S makes delta G more negative, meaning the reaction is more thermodynamically favorable. So in general, we say that a positive delta S is favorable. Again, that in and of itself does not guarantee that the overall process is favorable, but it contributes to it being favorable. And then if delta H, if delta H is negative, that also contributes to delta G being negative, because according to this equation, well, we're just starting with delta H. So, if that's negative, it makes delta G more negative. If that's positive, it makes delta G more positive. So, again, a negative delta H does not guarantee the overall process is spontaneous or thermodynamically favorable. Neither does a positive delta S, but they both contribute to the favorability in a favorable way. No pun intended. So, hopefully that makes sense, but I'm going to erase this here because delta H is not actually negative. I was just pointing that out as being a favorable condition. Okay, so that is that question. I'm going to make a separate video going through how to grade the free response. So I will grade my free response using the official answer key. I would recommend you trying this problem. Well, you've kind of already seen how to do it. But, for other problems, I would recommend you trying them on your own and then grading them using the answer key. And then I'm also going to show you in that video how some sample student responses and looking at how those responses were graded, which hopefully will be instructive in terms of seeing, getting a better idea for what the graders look for in responses, and then some common errors that can cause you to lose points. So, okay, see you there.